We are now going to characterize compactness in terms of open covers. The methodology of proof is exactly the same for the same result we showed for the real numbers. So if at any point of time things seem to be going a bit abstract and complicated, just look back through the proof in the real numbers to get a concrete feeling of what is happening. So let's begin with the definition, and these are all rather straightforward definitions because we have already seen it once. Definitions. Let X be a metric space and K subset of X. An open cover U of K is just a collection G lambda of open sets. I don't care what the indexing set lambda is. It could be finite, countable, uncountable. It could be anything. It's just a collection G lambda of open sets such that K is a subset of union of G lambda. I just take the union over the indexing set of all these sets. Okay. Now this is the definition of an open cover. Any subcollection of G lambda is said to be a subcover. Of K. Okay, so far so good. We say K is compact. If any open cover has a finite subcover. So you need to find a subcollection of the cover comprising finitely many sets whose union is also K. So this is the definition of compactness. Nothing new here. It's exactly the same. Now I'm going to show that sequential compactness is same as compactness, and again we proceed via an intermediary concept called the Lebesgue number. Now here is a place where I should make a point. Way back when we studied topology of real numbers and studied all this in real numbers, I had defined a Lebesgue number in a particular way that was just to make the proof simpler in that scenario. Technically what I defined as the Lebesgue number, it was not the correct definition. So please note what I'm going to define now is the correct definition of the Lebesgue number. Okay. So this is the correct definition of the Lebesgue number. You can now delete your earlier definition from your brain and empty the recycle bin also, so that this new fresh definition is what stays in your mind till you retire from active mathematical life. Let A be a subset of a metric space X. A Lebesgue number, let's just call it L for lack of creativity. A Lebesgue number L for an open covering U of A is any number, note this is not unique, is any number such that if X is in A, then B of XL is subset of G for some G in U. Okay, so what this says is that so sorry about that. I said that I'm going to change the definition and I gave the same definition again. Sorry. If X is in A and B subset of X is any set, not just a ball or anything, any set that contains X and is and satisfies diameter of B is strictly less than L, then B is subset of G, where G is some member of U. Okay, so it was rather fortunate that I began with the wrong definition. That was not intentional, I promise you. It was complete accident. The earlier definition, in the place of this B, what I have called B, we had B XL. Okay, that is incidentally of diameter 2L and not just L in general. That's of diameter 2L. It's not always true. For weird metric spaces, the diameter of that set could be 0. What this new definition is saying is that you don't need to just consider balls. You just take any set B with the property that it contains some point X. Okay, it could contain some point X in A. It doesn't matter what it is. And if its diameter is less than L, then it must automatically belong to some member of the open cover. Okay, so the definition is same in spirit but different in the details. Okay, now I'm not going to bother relating this definition with the earlier definition. There is an obvious relationship. One notion of Lebesgue number will also be the other, but the other way around will not be true. I'm not going to bother with all that, neither should you. But let me just make the remark that qualitatively what we did earlier and what we are going to do now are not that different. Okay, so let's now prove a sequence of results that finally get what we want. So first result, theorem. Let me dignify it and call it a theorem. Any sequentially compact set K subset of X has a Lebesgue number with respect to the covering U of K. So whatever covering of K you take, it will always admit a Lebesgue number, provided the set you start out with sequentially compact. Proof. So what we do is the following. Suppose there is no Lebesgue number for U. There is no Lebesgue number of U with respect to A. With respect to K. Now, to be completely consistent with terminology, there is any has a Lebesgue number with any compact set K in X and a cover. Let me just rewrite this definition in mathematically precise terms so that I don't confuse you even further. Let K subset of X be sequentially compact and U an open cover. Okay, then U admits an Lebesgue number with respect to A. So I mean, I just reversed what respects what in the statement that I gave earlier. This is the way I have formulated. There's nothing sacred or writing it exactly the way it is, but this just is to have consistent terminology so that we are precise. Okay, so suppose there is no Lebesgue number of U with respect to K. Again, I made a slight error here. This should be K. Okay, suppose there is this covering U which does not have a Lebesgue number with respect to K. What does that mean? That just means that none of the 1 by n's work in the definition of Lebesgue number, right? The only way by which this covering can fail to admit a Lebesgue number with respect to k is if none of the 1 by n's work, which just means that we can find sets En subset of x, En intersect k is non-empty, diameter of En is less than 1 by n, diameter of En less than 1 by n, such that En is not fully contained in any member of U. That's what the meaning of 1 by n not being a Lebesgue number means. Okay. Now, what you do is the following. Let xn be some element in En. Okay. Rather, let xn be some element in En intersect k. Let xn be an element in En intersect k. Then xn is a sequence in k and must have a convergent subsequence, right? Subsequence xn k converging to x, and this x must also be in k. Okay. Now here is the key thing. Since x is in k, we can find G in this collection U and R greater than 0 such that B of x comma R is fully contained in G. Why? Because U is an open covering of K, X is a point in K. That means we can find some element G in this open cover which contains the point X, but G is open. That means we can find some radius such that BXR is fully contained in G. How does this help us? Well, choose K so large that dxn k comma x is less than r by 2. Of course, we can do this simply because xn k converges to x. Okay. Now choose k even larger. Such that 1 by nk is also less than r by 2. So just choose this k so large that both these conditions are satisfied. The distance from x and k to x is less than r by 2. 1 by nk is also less than r by 2. Okay. Then observe that enk has to be contained in B x and k comma r. I want you to check why this is true. It's not really hard. And this is contained in G, which is contained in U. Okay. So this is an easy check to check that ENK is actually contained in, just wait a moment, I made a slight mistake. ENK is contained in BXR, which is contained in G, which is an element of U, a contradiction. Okay, so this is not really hard to show that ENK is contained in BXR. By hypothesis, BXR is contained in G, is a subset of G, and that is an element of U. So this shows that any sequentially compact set in a metric space must have a Lebesgue number. So we now have all the tools ready at our disposal to prove equivalence of compactness and sequential compactness. All the tools are ready, so we can show that both notions are equivalent. So let's begin the proof right away. I'm not going to dignify such an easy statement with a rigorous mathematical statement. I'm just going to show that a set K is compact if and only if it's sequentially compact and vice versa. So let's start with let K be compact and let Xn in K be a sequence. The goal is to show that Xn admits some subsequence that converges to a point in K. That's the definition of sequential compactness. Suppose no subsequence of Xn converges to a point in K. Okay. Now I'm going to make a statement that might seem a bit weird, but it is just a matter of sitting down and really understanding what suppose no subsequence of Xn converges to a point in K means. So I claim this means for each X in K we can find Rx greater than 0 such that only finitely many terms of Xn are in Bxrx. Okay. This is just capturing the fact that the sequence cannot get arbitrarily closed to any element of K, because if it does, then we will be able to extract a subsequence that converges to that particular point. Okay, so I'm just saying that no matter what point you take, you can find an Rx, a radius, positive radius, such that only finitely many terms of this sequence are there in this ball of radius Rx centered at X. Okay. Now, because this is true for every single point, the collection of such balls, the collection U, which is by definition B of xRx as X runs through K, is an open cover of K. Okay. Now this must have a finite subcover. Okay, I'm going to simplify notation a bit. So there is a finite subcover, so I can write K as a subset of B x1 R1 union B x2 R2 union ... B xk rk. So this compact set K will be contained in this finite union. I've just simplified a notation a bit. Technically I should write B x1 Rx1. I've just simplified it with the subscript 1 as there is no scope for confusion. Now this sequence Xn, this set is also a subset of this, which means by the pigeonhole principle, one of these balls must contain Xn for infinitely many choices of n. Okay, so again let me just go back here. I should clarify one bit here. I've written for each x in k, we can find Rx greater than 0 such that only finitely many terms of xn. So there is a scope for confusion only for, I will just rewrite this statement, only for finitely many choices of n, many choices of n, xn is in bxrx. The way I've written it previously, there is a slight ambiguity. Do I mean that there are infinitely many distinct points, or do I mean that there are infinitely many n's for which xn is in bxrx? So I have clarified it now, so it should be clear to you that we have obtained the direct opposite of our hypothesis. We have found by the pigeonhole principle that one of these balls must contain xn for infinitely many choices of n, a contradiction. So this concludes the proof that compactness implies sequential compactness. For the converse, assume that K is sequentially compact. Assume that K is sequentially compact, and our goal is to show that it's compact, and so we will take and let U be an open cover. Our goal is to produce a finite subcover. So what we are going to do is the following. We already know that sequentially compact sets admit Lebesgue numbers with respect to whatever covers, or I have already forgotten which way it goes. So I think this is the correct way. There is a Lebesgue number L of A with respect to U. I can find a Lebesgue number for this open covering. Now this just means that if x is in K, then B x comma L by 2, this is going to be contained in some element U, which is an element of U, right? This is just the definition. I'll just call this U1. Okay, I will just call this U1. So what you do is the following. Just a slight change. What I'm going to do is, let A1 be an element of K. If you don't mind, let me make a slight change that will make my life and your life easier. Let me put a 2 here. I've just made this 2L. Let 2L be a Lebesgue number of A. Note, the reason why I'm doing this, any number lesser than a Lebesgue number is also a Lebesgue number. So let A1 be in K, then by what I just said, BA1L is going to be a subset of U1, which is going to be an element of U. Okay, there's going to be some U1 in this open cover U that contains the entire ball of radius L centered at A1. Now suppose K minus B A1L is non-empty. So here is the idea. I want to extract a finite subcover of this cover U in some manner. What I'm doing is I'm going to do the naivest thing possible. I'm going to take a given point A1 in K. Then I know that by the fact that this cover has a Lebesgue number, I will be able to find a U1 which contains the ball of radius L centered at U1. If it so happens that just BA1L encapsulates the whole of K, that means U1 also encapsulates the whole of K, which just means that I can just stop this procedure. But if K minus BA1L is non-empty, we can continue. Choose A2 in K minus BA1L and U2 in U such that BA2L is a subset of U2, which is an element of u. Exact same thing I'm doing. Now, if at some finite point this process, I'm going to repeat this. If at some finite point this sequence, if at some finite point I'm unable to choose any more points, or in other words, if those finitely many balls ba1l, ba2l, dot dot dot, bakl, if they happen to cover k, then I cannot proceed any further. I have found the required finite subcover, that's just u1, u2, dot dot dot, uk. On the other hand, if it happens infinitely often, so repeat this, if the process does not terminate, we can find a sequence, a1, a2, dot 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 in k, right? We can find an infinite sequence. Not only can we find an infinite sequence, we can find an infinite sequence with a very peculiar property that dai aj is greater than or equal to L for all I not equal to j. If you take 2 points in this sequence, they will be at least this Lebesgue number apart, and that's just by the way we constructed. For instance, just to see this, we chose a1 and we chose a2 coming from k minus the ball of radius L centered at a1. Therefore, the distance between ai and aj must be at least L. Okay. Now, what this shows is that no subsequence of an can possibly converge, right? This is simply because any term in this sequence is at least L distant away from any other term. So no, the same thing will be true for any subsequence, and the subsequence therefore cannot be Cauchy, okay, which just means that it cannot be convergent. Okay, now what does this tell us? This tells us that this process must terminate. Which is just a fancy way of saying U has a finite subcollection that covers K, right? So again, the proof is not really hard. It just uses some basic ideas about Lebesgue numbers, and we will be able to conclude that K is compact. So K is compact. We have now shown both directions, that K is compact if it's sequential compact, and K is sequentially compact if it's compact. So we have characterized compact sets in several ways. In the next video, we will try to get a version of the Hein-Borel theorem that is true for all metric spaces. As we have already seen, the Hein-Borel theorem is not true in all metric spaces. We were able to show it for Rn, but we have still not explored what is the correct version of Hein-Borel theorem for metric spaces. For that, we need something called total boundedness, which is the topic of the next video. This is a course on real analysis, and you have just watched the video on open covers and compactness.